Hi, now we are analyzing csir June 2014 chemical sciences. Just look at the given problem. The correct order of basicity for the following anions is. Here we have given with 3 anions, and to give answer for this problem we need to convert each of the given anion or base into its conjugate acid, and from the concept of conjugate acid base pair, by analyzing acidity of taken conjugate acids we can find the order of basicity for the given anions. Okay, right, as we know here the conjugate acid base pair have a difference of one proton. You can observe it. Okay, right, now just check the acidity of the taken conjugate acids of respective anions here. And if you look at the conjugate acids, they are having two substrains, hydroxy group and NO2 on benzene ring, and in those substrains hydroxy group is a strong ring activating group. Whenever a strong ring activating group is present on the benzene ring, it direct new electrophile at ortho or para positions with respect to that strong ring activating group like hydroxy group here. Okay, right, and if you look at the third compound, the new electrophile is at meta position and it is not a favorable place to take its place at the meta position of that particular electrophile with respect to hydroxy group. Okay, right, and whenever the electrophilic substitution reaction is more possible, then the hydrogen easily cleaves from that compound, and that compound has greater acidity. Okay, now here in between 1 and 2 conjugate acids, they are readily involved in electrophilic substitution by donating lone pair of electrons and oxygen to the ring. In that case, hydrogen easily cleaves as H plus to compensate the positive charge on oxygen. Okay, right, that's why they are having greater acidity when we compare with the second conjugate acid, because in the second conjugate acid the new electrophilic substitution reaction at meta position is not favorable. That's why the hydrogen cannot be cleaved easily from that. That's why the second conjugate acid has less acidity, okay, or less acidic in nature. Okay, right, now by this information we can say that whenever a compound has a less acidic nature, then its conjugate base has greater basicity. That's why the second anion should have greater basicity whenever we compare with first and the third anions. Okay, now we need to check the strength of acidity of first and third conjugate acids with respect to given anions. Okay, right, and if you look at the first conjugate acid here, there is a possibility of a 6-membered cyclic transition state with lone pair of electrons and oxygen of nitro group and hydrogen of hydroxy group. Okay, so in that case, whenever a 6-member transition state is possible, then that gives a stable product by cleavage of hydrogen as proton readily. Okay, that's why here the first conjugate acid should be with greater acidic nature when we compare with this para compound. Okay, so whenever more acidity on this first conjugate acid, then its conjugate, or then its base should be with least basicity. That's why in 1 and 3 anions, the first anion should be with least basicity, and that's why here the second anion having greater basicity whenever we compare with the third one, and the third one is having great basicity with respect to first anion. Okay, so now just check the option. So the first option, second anion, is having greater basicity than third, and third greater than first one. Okay, right, next one, the major product formed in the reaction of 2,5-hexane dione with P2O5 is. Okay, here you can write down 2,5-hexane dione into the structure, and whenever you just look at the structure, we can convert, or by flipping the single bond, so we can make it in the arrangement to form a furan. Okay, so whenever this 2,5-hexane dione reacting with P2O5, it result furan. So it is a named reaction of heterocyclic compounds, that is Paul-Knorr synthesis of furan. Okay, right, just check the mechanism of it. Now the absolute configuration of two stereogenic chiral centers in the following molecule is. Okay, here we have given it a molecule. We need to find the absolute configurations at 5 and 6 carbons. Yeah, here first we need to label the carbons to get the particular carbon, chiral carbon with absolute configurations. Okay, now according to IUPAC rules, we need to start from the functional group, that is keto group here, and followed by the nearest another functional group, that is alkene. So numbering should be from 1, 2, 3, 4, 5, 6. Okay, so we have chiral carbons at 5th and 6th carbons, and they are at 5th carbon here. So this is 5th carbon and this is 6th carbon. Okay, so that is from the IUPAC rules. Now at 5th carbon, if we try to give absolute configuration, first we need to give the priority order for the 4 different substituents on that particular chiral carbon. Okay, now here the competition for this carbon and this carbon, because here you can see that we have one double bonded carbon and one is single bonded carbon here. That means, as we know, if we have given with double bonded carbon, that's simply indicating that there is a presence of 2 carbons. Okay, now by that consideration, on this carbon we have 3 another carbons. Okay, now just look at this carbon. On that carbon we have 2 carbons and another carbon. Okay, so here is also 3 carbons. Now there are same carbons, and if you look at this carbon, we have only 2 carbons here. So competition is for these 2 carbons. Now we need to check for another level. That means we need to count a priority for next atoms. So here in this we have hydrogen, 3 hydrogens and 2 hydrogens here. At the same time, if you look at this carbon, in that we have CH3 and CH2CH3, and another carbon is containing keto group, that means oxygen, a double bond. That means this carbon should have a greater priority or a higher priority whenever we compare with this carbon. Okay, so that's why here first priority for this, and second priority for this carbon, and third priority for this carbon. So now just check the priority order. So it is simply clockwise direction, and here we need to check for the 4th priority group. So it is above the plane, that is hydrogen, and which is above the plane, because this branch is backside to the plane of it. So hydrogen is above the plane. Whenever least priority group is above the plane, then we need to take opposite absolute configuration regarding to that particular priority order. So here we have clockwise direction, then we need to take opposite configuration, because the least priority hydrogen is above the plane. That's why here it should be yes. Okay, at 5th chiral carbon, the absolute configuration is 5s. Okay, right, now just check 6th carbon. On the 6th carbon, first priority for this keto group, and next priority for this group, and third one this. Okay, so methyl group gets 4th priority. Now just check the priority order. It is anti-clockwise direction, but least priority methyl group is above the plane. That's why we need to take opposite absolute configuration for the priority order. So it should be R. So now just to give the absolute configurations at 5th and 6th carbons, simply third option is the correct. So 5s and 6r. Okay, right, next one, the correct statement about following molecule is. Here we have given with ANSA compound or cyclopane, and in this molecule is chiral and it possesses a chiral plane. That means here we can give a chiral plane on that bottom benzene, which is having more number of atoms when we compare with this benzene group. That's why, so that benzene having chiral plane. So our option 1 is the correct answer. And to get complete information on these ANSA compounds and chiral planes, okay, so just check the lecture in your course. Okay, right, by searching chiral planarity. Okay, right, next one, consider the following statements about cis and trans decalines. Here, as we know, just cis isomer undergo ring flip, and trans isomer is more stable than cis isomer. So here 2 and 4th options are correct. So that means option 1, B and D are correct. Okay, here I have given with A, B, C, D labels. Okay, so just consider second option and 4th options are the correct statements regarding cis and trans decaline, because just to try to draw their structures. So this is a trans decaline. In the trans decaline, we have two axial hydrogens, okay, and there is no possibility for ring flipping because equatorial bonds are with the cyclohexane chair conformations. That's why we cannot flip this trans-decaline, okay. So that's why it is stable, okay. Trans-decaline is more stable than a cis-decaline because you can see that in cis-decaline, so here, so this is the structure of cis-decaline, and in that cis-decaline you can see stronger steric repulsions are possible here. That's why it is not stable, or it is less stable when we compare with trans decaline, okay, right. And here in cis decaline you can see that axial and equatorial hydrogens, whenever axial equatorial hydrogens are possible or present on the decaline, then ring flipping is also possible on this cis decaline, okay. That's why here in the given statements, the second statement, trans isomer is more stable than cis isomer, and cis isomer undergoes ring flip, or correct statements, okay, right. Next one, in bis dimethylglyoximate nickel 2, the number of nickel nitrogen and nickel nitrogen and nickel oxygen and intramolecular hydrogen bonds respectively are, okay. First thing, we need to know the structures of ligands, okay. Here we have given with dimethylglyoximate, so this is dimethylglyoximate structure, just observe it. Now just check the complex of nickel plus 2 here. So in that you can see nickel nitrogen bonds are 4 and nickel oxygen bond is 0, and hydrogen bond between hydrogen and oxygen or 2, okay. So here is the one and here is the one. Yeah, next one, among the following species, A, nickel 2 as a dimethylglyoximate, and B, aluminum 3 as oximate, and silver 1 as chloride, those that participate with urea hydrolysis method are, okay. In this nickel 2 dimethylglyoximate and aluminum 3 oximate are precipitated under or in during the urea hydrolysis method, okay. Whenever the transition metal with nickel and nickels and some other metals like aluminum having the ligands like dimethylglyoximate oximate are involving in urea hydrolysis method, okay. Next one, in an enzyme fixes N2 in plants by evolving hydrogen, the number of electrons and protons associated with that respectively are, okay. So here just to look at the reaction, N2 reacting with other means N2 with 8 protons and 8 electrons and 16 ATP. By using 16 ATP and 8 electrons are involving in this reaction of nitrogen fixation to produce ammonia. So answer is 8 plus 8, okay. Next one, the particles postulated to always accompany the positron emission among. Here just look at here, whenever the molecules are the nucleus containing more number of protons, then the proton decay takes place. In that case, simply positron emission with other particles like neutron and neutrino, that is electron neutrino, okay. So this is electron neutrino. In that neutron we have electrons and leptons, that's why. So in the answer, neutrino and electrons are the other particles which emit with positron emission, okay, right. And you can also see that whenever more number of neutrons present on the nucleus, then it emit electron, that is beta particle, and antineutrino and protons, okay. So in this case you can see beta particles are with antineutrinos, okay. Just remember that extra point. Next one, toxicity of cadmium and mercury in the body being reversed by proteins mainly using the amino acid residue. Here simply cysteine can be used because cysteine, that means sulfur, here you can see thioalcohol, the sulfur binds with cadmium and mercury, that's why here the cysteine amino acid is used, okay, right. Next one, nickel bromide reacting with ethyl diphenyl phosphine at -78 degrees centigrade in carbon disulfide to give red compound A, which upon standing at room temperature turns green to give compound B of the same formula. The measured magnetic moments of A and B are 0, 3.2 Bohr magneton respectively. The geometries of A and B are, so we need to find square planar, tetrahedral or tetrahedral octahedral. Just check all the 4 given options, okay. Right, first thing, just write the given information. So we have nickel bromide, so which is reacting with ethyl diphenyl phosphine, then it resulting the product A or complex A, which is in red color with the magnetic moment value 0. So by just looking at the mu value equals to 0 Bohr magnetons, we simply know that complex having 0 unpaired electrons. Okay, now from the red compound it produces B complex, which is in green color, and where it is exhibiting mu value 3.2 Bohr magneton. As we know, to find spin only formula to calculate magnetic moment, we have the formula that is mu is equal to under root n into n plus 2. Here n equals to number of unpaired electrons, so the number of unpaired electrons may be 2 in this complex B. Okay, so whenever 2 electrons are there, the magnetic moment may be 3.2 Bohr magneton to 3.87. Okay, right. Now just look at nickel complex, where it is in nickel plus 2 oxidation state in nickel bromide. Yeah, whenever nickel in plus 2 oxidation state, it contains 8 d electrons. So this is the electronic configuration, but the unpaired electrons can get paired up here. Whenever the unpaired electrons are paired up, then we have a dsp2 hybridization. Whenever it is dsp2 hybridization, the structure is square planar. Okay, so whenever it is square planar, there are no unpaired electrons. That means mu value is 0. Whenever it is 0, the compound A must be square planar, and it is showing red color. Okay, right. And if you look at this normal electronic configuration, where you can see 2 unpaired electrons, in that case the 4 orbital, that means sp3 orbitals involved in hybridization. So whenever sp3 hybridization is there, that must be tetrahedral. Okay, so with the 2 unpaired electrons, it should show 3.2 Bohr magneton. That's why tetrahedral structure must be complex B. Okay, you can see the reaction here. And next one, the correct nonlinear and isostructural pair is in the given options we need to find. Yeah, just find here the hybridization for a particular component ions here. So in the HCl2, sulfur is a central atom. That's why we need to find valence electrons of it. So here it is having 6 valence electrons, and 2 of them involving a sigma bond with 2 chlorines, and other 4 electrons are 2 paired up electrons. Okay, yeah, here total sp3 hybridization with 2 lone pair of electrons, then it should be angular in structure. Okay, and just by the same process we can find that I3 minus. So I contain 7 valence electrons, and it is having minus, that means extra electrons. So total 8 electrons in the 2 with sigma 2 with 2 sigma bonds with 2 iodines, and 3 are simply paired electrons. So sp3d hybridization with 3 lone pair of electrons, it must be linear. Okay, so like that we can find for I3 plus and ClF2 minus. In that case you can see I3 plus angular and SCl2 is angular. That's why here our option must be the second one. Okay, right. Next one, ozone present in upper atmosphere protects people on the earth due to its diamagnetic nature and its color and okay, so diamagnetic nature, you can see here diamagnetic nature, and here its color. Okay, so due to its blue color, due to absorption of radiation of wavelengths at 255 nanometers by destroying chlorofluorocarbons. Okay, so just check all the given 4 options, and in that, so the correct reason is due to absorption of radiation of wavelength at 255 nanometer. Okay, so in that case the ozone layer, which is in stratosphere, absorb UV rays. Okay, and which filters that rays, and after filtering, the UV rays which are coming from the sunlight are harmless to the humans and other living beings on the earth. Okay, that's why here the option C is the correct answer. And the normal properties of ozone are, ozone is diamagnetic in nature and it is blue in color, but the perfect reason is simply third one. Okay, right. Next one, if L is a neutral monodentate ligand, the species like silver, tetracoordinate silver is given, and here octahedral silver is given, and here another with that means silver with tetra coordinator. In that case, it is in +3 acceleration state. Okay, so here we have given with different acceleration states of silvers with different ligand combinations. Okay, we need to find their correct para or their magnetic natures. Okay, yeah, if you look at this silver +2, that means silver with +2 acceleration state, and another with the +2 acceleration state. In that simply we have 9 electrons in its d orbital. Okay, whenever ligand is neutral monodentate ligand, so in these two complexes silver is exhibiting +2 acceleration state, and in that case it should have 9 electrons only in its d orbital. And whenever we fill the electrons in any way after ligand contribution, then simply one unpaired electron must be present in it. So whenever unpaired electrons are present, that complex must be paramagnetic in nature. Okay, right. And if you look at another silver complex where it is in +3 acceleration state, so it contains 8 d electrons, and there is a possibility of unpaired electrons to be paired up. Okay, so due to the heaviness of this metal, whenever we move down in transition metals, the electrons are possible to pair up whenever there is a possibility in that orbitals. Okay, now after pairing, then we have a dsp2 hybridization for that silver complex. In that case, this complex shows a square planar structure. Okay, and here you can see there are no unpaired electrons. That's why this complex of silver with +3 acceleration state must be diamagnetic in nature. Okay, right, just check the options. Now chromite ore on fusion with sodium carbonate given here. So whenever chromite ore reacting or with the sodium carbonate, simply it produces chromium ultimately. But in the first step you can see that Na2CrO4 and Fe2O3 are the products. Okay, that's why here Na2CrO4 and Fe2O3 are the correct term, and here option 1 is the correct answer. Okay, just check all the reaction here. That means complete reaction steps and to get the chromium extraction. Okay, right. Next one, the ligand S, that is or fluxional in the given iron complex, where we have given with neta5C5H5 and neta1C5H5. Okay, whenever the cyclopentadienyl, okay, dienyl ligand with neta5, then there is no possibility of fluxionality, because all the 5 carbons are involving or coordinating with that particular iron metal in the given complex. That's why there is no fluxionality, or we cannot find any flipping in it. But whenever the C5H5 with neta1, okay, neta1 or neta3, then the carbon can exchange. That means coordination of carbons of a cyclopentadienyl ligand can exchange rapidly, and we call that exchange of coordination to that central transition metal as fluxional behavior. Okay, that's why here neta1 C5H5 show fluxional behavior. Okay, that's why option 2 is the correct answer. And next one, the acceleration state of nickel and the number of metal-metal bonds in the nickel complex. Here we have given with a dimer, okay, nickel dimer, that are consistent with the 18 electron rule or. Okay, first we need to find the acceleration state on nickel, and here we need to find acceleration state on nickel. That's why here we have considered it as X, and here we have 2 nickel, that's why 2X plus, so 0, because each carbonyl ligand contributes 0, and that means that is neutral, and total charge is -2. So from that we can get X is equal to -1. Okay, right. Now so in that complex we need to find total electronic count. So here we have 2 nickel, that's why 20 electrons, and 6 CO contribute 12 electrons, and -2 contributing 2 electrons, so total 34 electrons. And here we have a formula to find metal-metal bonds, that is total electron count is equal to 18x minus 2y. Here x indicating number of transition metals in the complex, and y indicates number of metal-metal bonds. So here 34 into 18 into 2, because here we have 2 nickel, that's why 18 into 2 minus 2y. From that we can get number of metal-metal bonds equals to 1. That means each metal contributes 1 electron, so total 2 electrons and it is 36 electrons. Whenever 36 electrons are there, the complex is following 18 electron rule. That's why here oxidation state of nickel is -1 and number of metal-metal bonds equals to 1 here. So option 3 is the correct answer. Next one, cobalt complex with here which is showing red color, whereas another cobalt complex with the ligand L prime showing green color. We need to find correct that means two different ligands in the given cobalt complex with +3 oxidation states. Okay, right, to give answer for this problem we need to check VGR, that means VGR wheel here, and we have given that the first cobalt complex with ligand L showing red color. That means whenever it show red color, it should absorb green radiation. You can see that it is showing red, that means its opposite color simply green, that means it should absorb green radiation. At the same time, second complex showing green color, that means it should absorb red radiation. Okay, right, just check the strength here from that violet. So that means the wavelength is increasing towards red. That means a red light contain greater wavelength, okay, longer wavelength. At the same time, frequency starting from red and frequency, that means energy increases towards violet. That means violet has greater frequency. Okay, so here you can say that red color having least energy or lower frequency when we compare with G. So green color has greater energy or frequency. Whenever more energy is there in radiation, that ligand must be strong ligand. Whenever the energy is less or frequency is less, then that ligand must be weak ligand. That's why for the first complex which is showing red color should absorb green radiation, and that is possible whenever the ligand is a strong ligand. And the second cobalt complex is showing red color, and that means it is absorbing red radiation. That means the energy is very less, so for that weak ligand must be there in that complex. Okay, so that weak ligand must be water. Okay, next one, the structure of stibinum. So here we have given with stibinum, pentaphenyl stibinum and pentaphenyl phosphorus, okay, respectively, or we need to check their structures. Yeah, here stibinum complex or compound showing square pyramidal, whereas the phosphorus compound showing trigonal bipyramidal. So this difference in the same group of phosphorus and nitrogens in the phosphorus and stibinum in the nitrogen family is just due to difference in their sizes. Whenever we move from top to bottom in a group in the periodic table, a size increases. Okay, so that's why whenever size increases, the size simply makes planarity for that molecule. That's why a stibinum compound showing square pyramidal, whereas phosphorus is showing trigonal bipyramidal structure. Okay, next one, the typical electronic configurations of transition metal center for oxidative addition is. Okay, so just check the features of oxidative additions, and you can know that simply whenever the transition metal in a complex has a greater electron density on d orbitals, then they're ready to get oxidation. Okay, that's why here d8 and d10 electronic configurations on a transition metal center favor oxidative addition. Okay, right, next one, gelatin added during polarographic measurement carried out using dropping mercury electrode, so to reduce a streaming motion of a mercury drop. That's why statement 1 is the correct answer. Next, the pK values of following salt or aspartic acid are indicated below. The predominant species that would exist at pH 5 equals 2. Okay, so here we need to check that given aspartic acid, and that should be stable at pH 5. That means pH 5 showing that it is acidic conditions. So to be acidic, the given aspartic acid must be, that means the carboxylic acid groups must be in ionic form, that is COO minus H plus. Whenever they are in ionic forms, then pH maintains at 5. Okay, so that's why option 2 must be the answer for the given problem. Next one, the major product found in the following photochemical reaction is. Okay, just look at the reaction here. We need to find the correct one. Now in the reaction, in photochemical condition, 2 plus 2 cycloaddition possible, and which gives the final product where at the future carbons tertiary butyl group and hydrogen are on same side. That means they are cis to each other, because whenever they are cis to each other, then the fused carbons or fused rings are in bent like structure in that case. So all the groups are simply far away to each other. In that case, less steric repulsions we can observe in that compound. But whenever if the two groups on, that means tertiary butyl group and hydrogen on the fused carbons of the ring are present opposite to each other or trans to each other, then planarity of the fused rings can be observed. So whenever they are planar, then simply all the groups are near to each other, that means bulk groups are near to each other. In that case, simply steric repulsions will be more, then the molecule is not stable. That's why here these two groups must be same side. To escape from the steric repulsions, it get a bent form or bent like structure. Okay. Yeah, next one, the pair of solvents in which PCl5 doesn't ionize is, okay. So here you can see that PCl5 is a inorganic, a polar solvent. A polar solvent dissolves in another polar solvent only. That's why here you can see that third option contains a benzene and carbon tetrachloride. They are non-polar solvents, so PCl5 doesn't ionize in benzene and carbon tetrachloride. Next one, the major product formed in the following reaction is, just observe the reaction here, and you can see that there is a participation of neighboring group, that is a phenyl group act as a neighboring group, and so which is opposite 180 degrees opposite to that leading group, toxicity group. That's why neighboring group participation is more possible, and whenever neighboring group participation is there, then the stereochemistry retained in the product. That means whatever the stereochemistry present on the reactant, the same stereochemistry observed in the product in neighboring group participation. Okay, so that's why you can see that the ACO minus, that is nucleophile, gets the same place where toxicity group is cleaved. Okay, next one, the correct order for the rate of electrophilic aromatic substitution of the following compound is. Here we have three compounds. We need to find the correct electrophilic substitution reaction rates for them. Yeah, if you see that the second compound, which is having a heteroatom, that is nitrogen, and whenever you look at that nitrogen is more electronegative than carbon. That's why it always wants to drag the electrons of the ring. In that case, there is no electron density, more electron density on that other 5 carbons on that pyridine. That's why electrophilic substitution reactions are less favorable, or the rate of electrophilic substitution reaction is less on this compound. Now we need to check this chlorobenzene and substituted indole. And if you look at the chlorobenzene, and as we know, chlorine is a moderate ring activating group, that's why it favor electrophilic substitution reaction. So the third compound should be having a greater rate of electrophilic aromatic substitution whenever we compared with the pyridine, that means second compound. And if you look at the first one, whereas benzene is fused with another 5-membered ring and which is containing heteroatom nitrogen, and the lone pair of electrons on nitrogen involves in the ring to delocalize 5 bonded electrons and to make it aromatic. So that's why, so when the heteroatom nitrogen in that 5-membered fused ring involving, that means it is donating electrons to that ring, and which is increasing electron density on the benzene ring. So whenever electron density increase on the benzene ring, so electrophilic aromatic substitution reactions also more, that means the rate of electrophilic aromatic substitution is more. That's why the first compound has greater rate of electrophilic aromatic substitution. So what is the order now? 1 is greater than third one, and third is greater than second one. Okay, right. Next one, the commutator of the kinetic energy operator. Here we have given with the Tx caret, and the momentum operator Tx caret for the one-dimensional case is. Okay, so just check. So here for the kinetic energy operator, we have the operator as minus h cross square by 2m dou square by dou x square. For momentum operator, we have minus ih cross dou by dou x. Whenever these operators are working on function that is a psi, so just check all the possible steps. and you can get answer 0 for it. Okay, next one, the major product formed in the reaction of trans 1-bromo 3-methyl cyclobutane with sodium iodide in dimethyl formamide is. Okay, so just look at the compound. In that we have given with dimethyl formamide. Dimethyl formamide is a polar solvent, but it doesn't have any proton. That's why aprotic polar solvent. So whenever aprotic polar solvent with a strong nucleophile, that is I minus, and at the secondary carbon, that means secondary halide, SN2 reaction is more possible. Whenever SN2 reaction is more possible, the attack of nucleophile and elimination of leaving group takes place at a time, and attack should be from opposite side to that leaving group. So that's why here you can get iodine and methyl group or same side. Next one, when silicon is doped with group 5 element, so here donor level are created close to valency bond, and donor levels are created close to conduction band. Acceptor levels are created close to the valence bond, and acceptor levels are created close to the conduction band. Okay, so whenever silicon is doped with group 5, we know that silicon has valency 4, and whenever it is doped with group 5 contain valency 5 nearly. Okay, that means extra electron is there. That's why whenever extra electron is there, then it is called as n-type conductor. Whenever we see n-type conductor, a new donor level is created, and that donor level is near to conduction band, and the conduction takes place through the extra electrons. Okay, so that's why here the first one, that means that the donor levels are created and which are near or closer to the conduction band. So second option is the correct one. Whenever the same silicon is doped with the third group elements, okay, that means boron group elements, then so the electron scarcity, that means less number of electrons are there. That means through the hole conduction takes place. We call them as p-type conductors. Okay, just check them. Next one, the symmetry point group of propyne is. So this is the structure of propyne, and if you check the principal axis, which is going through 3 carbons and 1 hydrogen, and in that whenever we flip, so we can get C3 axis. Now we need to check for the planes here. So there is no possibility of horizontal plane, but there is a possibility of vertical plane. That means a plane which can pass through that principal axis. So here we can give point group C3V. Okay, right. Thank you.